Hey everyone, this is Chapter 14, Lesson 2. We're going to talk about the perimeter of a regular polygon. And this may sound like a silly thing for us to even consider because that should be one of the easiest things for us to find in math, right? Perimeter of a regular polygon. We already know that all of the sides of a regular polygon are equal because by definition a regular polygon is equilateral and equiangular. So if you know one side, you know them all, and then it's just a matter of adding or multiplying. So, for example, if I have an octagon, 8 sides, and each side is 3, well then 3 times 8 is 24. That's the perimeter of my regular octagon. Okay, so perimeter of a regular polygon can be super easy, provided that I know the length of the sides. So then we start to think of, well, what if I didn't know the length of the sides? What if I knew something else instead? And one of the reasons that we might think about this, besides the odd case in which you knew the radius or the apothem of a regular polygon, those terms that we talked about in the previous video, the radius and the apothem of our figure. Okay, so what if you knew one of those instead of the side? Unlikely, but still possible. That might be one reason we would look at other ways of finding the perimeter. But we actually look at a different reason here in the book. So if you see this figure here, this is a layout for an ancient Greek temple at Delphi. And it had 20 columns set around here. And a 20-sided figure is called an icosagon. This is a regular icosagon because these are all equal sides. Okay, they're placed equally. Now, as you can see from this figure, and as we saw in the previous lesson, no, not in the previous, well, here. This is just 10 sides, a regular decagon. And we can see how close to a circle we're getting with a regular decagon. And then we can see here how even closer we're getting with 20 sides. So because the icosagon has so many sides that it looks a lot like a circle, it started the idea in the minds of some mathematicians like Archimedes that maybe we could find a connection between a regular polygon, which is easy to measure, and a circle, which was much harder to measure. Because if you think of trying to find the perimeter of a circle by measuring the length of a side and then multiplying by the number of sides, well, that doesn't really work, right? You don't have any sides in a circle. But what you do have in both a regular polygon and a circle is a radius. So the attempt here is, what if we could make a formula for the perimeter of a regular polygon that doesn't rely at all on the length of the sides, but relies instead on the radius. And then we could use that to help us find a formula for the perimeter of a circle. Okay? So it's this whole idea we've had in geometry all along, just like with our deductive logic and our proofs of, if we know one thing, and whether that be a postulate or a definition, if we know one simple thing, can we use that to help us find something else to be true? And once we know that to be true, can we use that to find something else to be true? And more things can be developed through that process. So, what's one thing that we know really well by this time of year? That's right, triangles. So we're going to use triangles in our regular polygons to help us find a formula for the perimeter of any regular polygon. And then when we get to lesson 4, we'll be able to show the connection between that formula and the formula for the circumference of a circle, because the circumference is its perimeter. Okay, and we'll even get to see how pi was discovered. Okay, so let's take a look at a hexagon. Okay, just to show you we can do this with any figure. I also have an octagon here, because it won't depend on how many sides we have. It will just depend on it being a regular polygon, that all the sides are equal. And trace my little kid block here. Okay, so it wouldn't matter if I was using a hexagon, an octagon, a pentagon. Something that's true with all of my regular polygons. As we saw in our previous lesson where we were talking about all regular polygons being cyclic, is that I can take that regular polygon, and if I draw its radii, I can divide it up into triangles. Now these radii, just like the radii of a circle, are all equal. So I get congruent triangles as well. And you can see where they've started to do that here. I get a triangle, 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 triangle. 1, 2, 3, 4, 5. In this pentagon here, 1, 2, 3, 4, 5, 6, 7, 8. In my octagon here, the number of triangles is going to be the same as the number of sides, because each side is going to form the base of one of those triangles. Okay, so I can divide it into triangles. So then you can see how we can use our triangle knowledge to very easily find, for instance, the area, as we'll do in the next lesson. Because if I can find the area of one triangle, I can just multiply it to find the area of the whole polygon. And then also for the perimeter, if I don't know what this side is, but I know the radius, can I use that to help me solve for this side? Well, it turns out I can. You may not be pleased with how we do it because it does involve sine, but I'm promising you now, so that you do not panic, I will not put anything involving sine on the test. Okay, we are going to use this to show how we go from finding perimeter and area of polygons to finding pi. Okay, and that's going to involve using sine, and we're just going to use it in the homework here, but please don't panic. Okay, it's not going to be like doing it on the test. Most of it is going to be here in our explanation of it. Okay? Okay, so now that we've gotten that out of the way, I'm going to use sine. So you can see here, we have the radius, and then we've drawn this line here, which, remember, we called the apothem. And we said that the apothem is a line that's perpendicular to the side of the polygon. Okay? So it's perpendicular to the side, so it's going to form right angles. And we've done that here as well. Okay? So now, as I've done that, I have formed 2 right triangles within this big triangle here. Okay? I have 2 right triangles. So then I have the radius here, which if I had a circle, or if I didn't know my side length, perhaps this is the length that I know is my radius. Okay, we can see that here that the radius is also the hypotenuse of this right triangle that we've made. Okay, so then I have each of these sides we'll call S. Okay, it's a side of the triangle. And so then here we see that we've divided it into 2. So this is S over 2. Each of these little parts here is S over 2. It's half of S. Okay, so now, let me make that a little clearer there for you. S over 2. Okay, so this is cool. We've divided up into triangles, and we said that we had 8 of these big triangles going around here. Okay, So let's see how many we've divided them into. Okay, right? 8, and then if I divide them in half by drawing that apothem, then I would have 16, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. If I draw the apothem on each of those and divide them into nice little right triangles, I have 16 of these guys. Okay? So, I'm looking at this angle here in the middle because I have this right triangle. All around here, this is 360 degrees, right? So what would the measure of just this one little angle be? All right, I'm just going to divide it by the total number of angles I now have. So that's going to be 360 divided by the total number of angles times 2, right? I'm saying that here it'd be 16, right? I have 16 little right triangles that are just this side, but it's the number of sides, S times 2. Here, this is an 8-sided figure, so 8 times 2 is 16, but it's the number of sides times 2, okay? We could also simplify that down. Let's divide both of those by 2 and just make this 180 over S. Okay? So that would give us the measure of this little angle here. Okay? That gives us the angle measure for our triangle is 180 over S. Okay, and so that's just going to be based on the number of sides that I have. That's why it can work for any figure that I have. Okay? Actually, so that I don't confuse this, let's use N for the number of sides. N for the number of sides, and S will be the length of each side. Okay, then we're not confusing ourselves. Or I'm not confusing you. Okay, so 180 over N is the measure of our angle. This side here is just the side length divided by 2. And then this hypotenuse here is our radius. Okay, well, let's think about, I don't know anything about the apothem. And the thing is, I don't have to, because did we learn about a ratio that involves just the side opposite an angle and the hypotenuse? That's right, that is the sine ratio. Opposite over hypotenuse is the sine of the angle. So if this is my angle X up here, okay, then the sine of that angle is the opposite over the hypotenuse, okay? So I can start to put together a formula using this information. You are not going to need to remember this formula or how to do all this. I'm just trying to show you how we came up with the formula that we're using. When they give you this big complicated formula in the book for the perimeter of a regular polygon, I want you to know where that formula came from. Because that formula is going to help lead us to pi, okay, in our discussion of it. Okay, so we are going to now say that I have the sine of, our angle measure was 180 over n. So sine of 180 over n is equal to the opposite, s over 2, over the hypotenuse, which is r. Okay, we've started on our way. I'm going to stop the video here and do a part 2 because I think I can only upload 15 minutes at a time. So come right back for part 2.